Let's try solving problem 43 here from section 3.3. We started by graphing this thing and looking in the interval 0 to 4 pi. When we looked at the graph, we expected two solutions in that interval. So we'll kind of keep that in mind as we work through things. Now, like we did the last problem, we're going to start by undoing the sine function. And what undoes the sine function is its inverse. I'll apply that to both sides. On the left-hand side, the sine and the sine inverse cancel each other out. I'm left with theta over 2 equals sine inverse of negative root 3 over 2. With the sine inverse, let's keep something in mind. Sine inverse is going to give you a value in this range, negative pi over 2 to pi over 2. That's the range for the inverse sine. So in particular, we want to know where the inverse sine has a value of negative root 3 over 2. So that's down here someplace. So y equals negative square root of 3 over 2. And you can see that there's two places where that line crosses the x-axis, or excuse me, crosses the circle at two different angles. Now when you do this on your calculator, if your calculator was in, say, degree mode, it's not going to give you this angle. It's going to give you a negative angle. So let's do inverse sine. Why does that seem really, really small? Let's try it again. Inverse sine of negative square root of 3 divided by 2. Now this is in degrees because I probably wouldn't recognize the angle in radians. And I get negative 60. So that's one of these angles. I got to do a little bit of work here. That's negative 60 degrees, which is positive 300 degrees. What is it in terms of radians? 5 pi over 3. So 5 pi over 3 is one of our angles. Now keeping in mind that this was negative 60 degrees, that tells you something about this angle as well. That angle is positive 60 degrees. So that means that over here we're at 180 plus 60, or 240, and 240 is 5 pi, or 4 pi over 3. So this one little problem has two possible solutions. 4 pi over 3 and 5 pi over 3 are the possible answers that you can get from the inverse sine of negative root 3 over 2. So theta over 2 is going to be, let's start with 4 pi over 3 plus, and this is going back to our conversation earlier, Michael, multiples of 2 pi. So that's one possibility. The other possibility is that theta over 2 could equal 5 pi over 3. Again, with adding in multiples of 2 pi. This gives you the most general solutions that you can get. Okay, let's solve for theta. What do I have to do to get theta by itself in each of these equations? Multiply by 2. Thanks, Rami. So multiply by 2 times 2 times 2. That's going to cancel out. I'll get theta equals 8 pi over 3 plus 2 times 2. It'll be k times 4 pi. So I'm just putting the 2 times 2, I'm putting it in here. Likewise, over here, I can get theta equals 10 pi over 3 plus multiples of 4 pi. Now I'm going to do something that I didn't do in the previous one. I'm going to bring these together. What would a common denominator for these two fractions be? 3, right? So this is 8 pi over 3. If I multiply by 3 over 3, I get k times 12 pi over 3. And bringing these together with a common denominator is just going to make my life a little bit easier. So all together, I'll get 8 pi plus 12 times k times pi over 3, and 10 pi plus 12 times k times pi over 3. These are the most general solutions that you can create. If you plug in values for k, k being some integer, you can get any solution that would exist for this equation. Let me pause for a second before we do the last little bit. Is there something that I can help out with up to here? Mary?
I'm just confused algebraically why you would be able to multiply, like when you multiply 2 on both sides, why the k doesn't have a 2.
Well, you only multiply once. If you had an addition or subtraction, then yeah, you would have to distribute. But when you multiply, so for instance, if I had 6 times 7 times, let's do it this way, 10 times 6 times 7, you'd only multiply the first one, right? You go, all right, well, that's 60 times 7 is 420. The other possibility would say, oh, well, that's 60 times 70 is 4,200. But that means you're distributing when you shouldn't be. You would only distribute if there was an addition. If there's an addition, then yeah, both of them get multiplied. But if there's not, then just one of them gets multiplied.
And you get to choose which one.
Yeah, I mean, I could have left the 2 out, here in front, but I just chose to bring it together with this. 2 times 2 is 4. It was just easy to put together there.
Yeah.
Okay. All right. Was there anything else? The last little piece of this is that they want 6 solutions. They don't want the general solution. They want 6 particular solutions. So what we're going to have to do is plug in some values for k. So we'll make ourselves a little table, k and theta. Now you're free to plug in any values for k that you want. You could plug in k equals 3,208,306, but it might be a little bit messy. How about some simple values? Any suggestions? 0. Yeah, let's start out with 0. I mean, you don't get bonus points for coming up with really, really hard solutions. It's just another solution. So we'll do 0, I don't know, 1 and 2. If k is 0, then we get 8 pi over 3 or 10 pi over 3. Those are the 2 solutions we saw on our calculator. Those are the solutions in the range of 0 to pi. What if we put in k equal 1? Then what would I get? Leah? Cassie, what would we get if we put in k equal 1? Well, let's see, it'd be 8 pi plus 12 pi over 3. So it'd be 20 pi over 3, right? 20 pi over 3. Yep, and 22 pi over 3. Good. And we just need to do one more. You could choose k equal 2, k equal 1, or maybe k equal negative 1, etc. If we choose k equal 2, then what will we get? All right. Thank you. I didn't necessarily mean to pick on you again. All right, but that's okay. Cool. And then the last one here, that'd be 34. Yeah, 34 pi over 3. So here's your general solution right here. And these are your particular solutions. So, particular solutions, and then your general solution. How are we looking on that one? Okay? Yes, sir. If I mean, there's a chance I could ask for both. I mean, it just depends on, how I write the question. But the way the question's written in the book, they want both. All right, so I guess that's what I'd be prepared for. If I ask for less, then it's a bonus. Other questions on that one? Mm-hmm.
So that's the only time you have to do that is when they exist.
Yeah. What's different about this one is they're asking for general solutions, and then they want 6 particular solutions. In fact, if I was asked for solutions in the range of 0 to 2 pi, there wouldn't be any, right? Because none of these are in the range of 0 to 2 pi. We had to go up to 4 pi before we saw any solutions. So we can kind of compare things now. Let me see if I still got that graph someplace. Let's see. Window. Oh, I changed my mode. That's why it doesn't look so good. So I can compare things now. I got solutions at 8 pi over 3. Let's do this. This is kind of clever. It's a nice little trick for you. If you hit the trace button, you can trace any particular value of x that you want. For instance, x equals 4 or x equals 5, etc. But I want to see where the graph is when x equals 8 pi over 3. So if I type in an 8, then it'll open up a line down here in the bottom row of my calculator. Pi divided by 3. Watch what happens when I type this in. Where does that value of x land? Right where they meet, right? Which is exactly where they're supposed to. So, and you can repeat that for x equal 10 pi over 3. And it should find that other point. All right, good deal. Let's try another one similar to this. This would be a good follow-up. Problem number 42. Bless you. Maybe we should do problem number 40 instead. Because Michael, yours was very, very similar to 42. All right, so let's do 40. Sine of theta equals, we're going to have to make that sine of 3 theta. So this is problem 40-ish. Sine of 3 theta equals square root of 2 over 2. We're going to start out similar to what we've done with these previous ones. And that is we got to undo or get rid of the sine of theta that surrounds, or the sine that surrounds the 3 theta. So I'll take the inverse sine of both sides, square root of 2 over 2. I think the numbers on this one will be a little bit friendlier. What happens on the left-hand side? They cancel, right? So I get 3 theta. Now on the right-hand side, we've got to go back and think about, well, where does the sine equal square root of 2 over 2? Because basically that's saying sine of theta equals, or sine of something equals square root of 2 over 2. Sine is your y coordinate. So that means that you're going to get solutions in the first and second quadrants. Your calculator can help you out. In fact, your calculator will give you one of these solutions. When you look at the graph of y equals square root of 2 over 2, it's going to intersect our graph at two places. And those two places are pi over 4 and 3 pi over 4. So theta equals pi over 4, or 3 theta equals 3 pi over 4. But there's another little thing that I'm missing here. Sine is periodic with period of 2 pi. So I've got to put in the plus multiples of 2 pi. And it's this term here that's going to allow me to generate multiple solutions. It's going to give me the general solution and then any particular solutions I want from there. Now I'm adding this on because sine is periodic with period 2 pi. If I was dealing with a tangent or cotangent, tangent and cotangent have different periods. Period of tangent and cotangent is pi. So I'd have k times pi as opposed to k times 2 pi. We'll do one like that, maybe two. The rest of this is just to solve for theta. So what do I have to do to solve for theta? Yeah, multiply by 3, or divide by 3, or multiply by 1/3. So 1/3 here, 1/3 here. Distributing itself to all terms, I get theta equals pi over 12 plus k times 2 pi over 3, or theta equals pi over 4. Maybe I should leave. I'm not sure if I want to reduce it or not. Let me not for the moment. 3 pi over 12 plus k times 2 pi over 3. Yeah, I don't see any reason not to reduce it here. Let's do what we did with the last one, and that is get common denominators for both of these things. So common denominator here would be 12. That means I'm going to multiply this by what over what? Come on, make me look good. Thank you, 4. So multiply by 4 over 4. All right, so 4 over 4. And pi over 12 plus 4 times 2 is 8. K pi over 12. You know, I'm not sure I really, you know, we are going to need 12 as a common denominator here eventually, so let me just continue with this. That's 3 pi over 12 plus, again, I'm going to have to multiply by 4 over 4. And I get 8k pi over 12. These are common terms now. They have common denominators, so I can add the numerators. Pi plus 8k pi, or 3 pi plus 8k pi, both over 12. These are your general solutions. You can get any number of solutions you want from here. So we can plug in integer values for k and get as many solutions as we need. Let's do what we did the last time. That is find 6 particular solutions. So we'll substitute in Just for variety here, let's substitute in -1, 0, and 1. We'll start by substituting in 0. Gives me pi over 12 and 3 pi over 12, which reduces to pi over 4. If I substitute in -1, what would I get in the numerator there? How many pi's would I have? Yeah. So here's a different take on it. If you factor out the pi, you're left with 1 plus 8 times k. 8 times -1 is -8, plus 1 is -7. So I end up with -7 pi over 12. And let's do that same trick over here. I'll factor out the pi. It's going to be 3 plus 8k. And if I plug in a -1 here, what's this quotient going to be? Tiffany, if I plug in a -1 for k? Oops, I should put a k here, not a theta. Yeah, -5. So -5 pi over 12. Last but not least, let's plug in a k equal 1. If I plug in a k equal 1 here, I get 9 pi over 12, which of course reduces to 3 pi over 4. And then over here, 11 pi over 12. And that's it. Good. You could probably plug in, let's see, could you plug in k equal 2? Yeah, you could probably plug in k equal 2 and get some more solutions that are still in the interval 0 to 2 pi. Are you getting a little more comfortable with what we're doing to get, first of all, our general solution, and then these are the 6 particular solutions. A couple nods, a couple blank stares, a couple people wishing they were elsewhere. All right. Let's try this one last time, except this time with a tangent problem. Yeah, thank you. Oh, this is theta. Theta is this, or theta is this. So here's k, here's theta. Thank you. Anything else? Sure? Doing good? Yeah. Would you tell me if you weren't? You weren't? Oh, okay, that's good. I was expecting you to say no. All right. Well, let's back up to problem number 20 then. And what you're going to see here is kind of a little bit of redundancy, but a little something new as well. Got the tangent of 2 theta equals 1. So problem 20. Tangent of 2 theta equals, is it 1 or -1? -1? Thank you. -1. Some of this should be getting to be a little familiar. How would you suggest I start out on this one? What's a good way to start out? Inverse tangent. Excellent. So we'll do the inverse tangent of the tangent of 2 theta equals the inverse tangent of -1. Okay. Well, on the left-hand side, this is 2 theta. On the right-hand side, the inverse tangent is kind of like the inverse sine. It's going to give you something between -90 and 90. Now, if you punch it in your calculator, you get -45 or -pi/4. Or better yet, you'll get 7 pi/4. But there's something a little bit different about the inverse tangent. or the tangent in general. Tangent is, yeah, it's period. What's the period for the tangent? Pi. Yeah, some whispers of pi. Good job. So I think we can probably just get away with this right here. Plus k times pi. Now, how come we're using pi as opposed to 2 pi? It's because of the period of the tangent. Tangent repeats itself every pi units, not every 2 pi. Okay. Let's follow through the motions that we've done with the rest of these. We're going to solve for theta. Multiply both sides by 1/2. That's going to give me theta equals 7 pi over 8 plus k times pi over 2. And I want to squeeze this together to get me one nice solution, or one nice expression here. So part of that's going to mean getting a common denominator. What's the LCD for something like this? 8. So once again, I'm going to multiply by 4 over 4, and I'll get 4k times pi over 8. These have common denominators, so I can add their numerators. And let me do one extra step here. In the numerator, let's factor out the pi, just to try and unmuddy the waters a little bit. That's going to leave me with 7 plus 4 times k. This is your general solution. Now, we're supposed to solve this in the interval 0 to 2 pi. Let's see if we can't figure out how many solutions we expect. I'm just going to do the graph up here as opposed to on my calculator. Let me graph, what is it, -1 and the tangent of 2x. Tangent of 2x. Okay, so starting at 0 and going up to 2 pi, how many solutions do I expect? 1, 2, 3, 4. So if you were to graph this on your graphing calculator, you could expect 4 solutions. You should expect 4 solutions in the interval 0 to 2 pi. It corresponds to this graph, right? So let's take a look at it. Nick, something's bothering you. You're like, wait a minute, I didn't expect that. All right. Well, you don't have to see it in your head. You can see it here on the graph. There's 4 that we expect. So let's see if we can't find those by plugging in different values of k. So let me go back to this here. And we'll make ourselves a little table. Here's k. Here's theta. What would be some values of k that we could choose? What's the easy one we're always going to start out with? 0. So let's start out with a 0. If k equals 0, and I think I like factoring out the pi here. If I put in a 0, what's left in the parentheses? 7. So I'm left with 7 pi over 8. So that's clearly one of the solutions. What else could I choose for k? 1. All right, good. So if I choose 1 for k, 7 plus 4 is 11. All right, so 11 pi over 8. Now until this fraction here, 11 over 8 in this case, or 7 over 8 in the other case, until it's bigger than 2, we're okay. It's not outside the range of 0 and 2 pi. How about if I go up to 2? If I put in a 2 here, then what would I get? 15 pi over 8. Is that outside my range? No, we're still good there. Do you think I can get away with 3? Yeah, if you tried a 3, you'd end up with 19 pi over 8. And since 19 over 8 is bigger than 2, we've gone too far. But despite Nick's intuition, we know we expect 4 solutions. So how am I going to get another solution? -1. Well done. So if we type in, or if we plug in -1, then let's see what we get. Well, that would be 3 pi over 8. So there's all 4 of our solutions. We got the general solution and the 4 particular solutions. All right. Looking good on that one? Okay.
Can you explain again how you are able to predict the number of solutions?
Sure. Our equation was this right here.
Yeah.
Tangent of 2 theta equals -1. So what I did is I graphed 2 things. I graphed y equals tangent of theta and y equals -1. So those are 2 separate graphs. This one and this one. And the number of solutions is the number of places where these graphs intersect each other. So if I look at the graphs, then I expected 4 solutions right there. 1, 2, 3, 4. In fact, Desmos is pretty nice. If your answers end up on nice integer or fractional multiples of pi, then it'll tell you what the coordinates are. And you can see that the coordinates match what we got. Good question. Anything else? Yeah, please.
Can you explain why tangent wasn't the 2 pi again? If you go back to that.
Sure. In fact, not even sure I need to go that far. Let me just dim this and let's type in y equals tangent of x. Let's take a careful look at the tangent graph. You can kind of see that tangent starts out here at 0, 0, and then it builds up, and then kind of down to the right. Now, this graph repeats itself starting right here, right? You're at the same point. Now, that distance is pi. That's how far it repeats itself. If you compare that to the cosine or the sine, let's put in the graph of the sine, y equals sine of x. How far do we have to go before the sine repeats itself? Well, 0 is here, and the graph starts repeating itself, not again until 2 pi. So its period is a little bit longer. So when you're solving these problems, trying to find general solutions and then particular solutions from them, when you're dealing with a tangent or cotangent, you're going to have to use a period of pi. You're going to have to use k times pi. And when you're doing sine or cosine, it's going to be 2 pi. All right? Same thing with secant and cosecant, but those are just inverses of those anyways. Nice.